Mahesh Chowdhary. I'm part of STMicroelectronics. I'm based in Santa Clara, California. Today I'll be talking to you about on-sensor and no-code tiny machine learning. So here is the Here is the agenda. So we'll walk through intelligent sensors, their past, their present, and some thoughts about their future. Then the next section I'll talk about on-sensor intelligence with machine learning core. This is something that we have in sensors from STMicroelectronics that are in production and many products in the market that have been produced using this concept. Then I'll talk about AutoML for on-sensor tiny machine learning. I'll briefly touch flexible intelligent sensor processing unit. And then, I'll walk you through the low-code, no-code tool, which is called as MEM Studio, with an example. So thereby, you will have a full picture of how to develop a solution and develop this using the sensor with machine learning core. So let's dive into this particular topic of sensors and their past. So MEM sensors, they've been around for a while. The very first patent on MEMS devices was filed in early 1960s. And this was an invention of resonant gate transistor, which was used as a frequency filter for ICs at that time. But you started to see these devices in real products in early 2000s. So there was a famous company, one that's out of Japan, that built this device, which had a gaming controller. And it had an accelerometer embedded in the gaming controller. So you can all guess which company it is. And you could play tennis with it, you could go bowling with it, you could do all of those. Your television screen gives you the input, and you have the, so I'm talking about Wii, Nintendo Wii. So that was the very first such product that was built with these MEMS sensors. Then in 2007, another famous company built this first full touchscreen phone. And in this phone, an accelerometer was used. And the function of that accelerometer was only to detect portrait versus landscape mode, and thereby rotate the screen. So you can guess which company it is, and that is, the first product was iPhone. And it used a MEMS accelerometer in it to detect portrait versus landscape mode orientation. And that's how the journey started. Then in 2008, an IMU was added to this gaming controller to detect more complex motions. So as you can see, these sensors started out with something fairly simple, where sensor was connected to a microcontroller. Sensor would output raw data. So there would be some signal conditioning. So sensor essentially had a sensing element and an ASIC. So this ASIC would do the signal conditioning and data acquisition, of course. And all the logic to do anything, sensor fusion, determination of portrait versus landscape, all of that was done on the microcontroller. But then, as the algorithms matured, many of these algorithms started to get added into the sensor. So the paradigm was, you start with sensor that's connected to microcontroller, all the logic sits on microcontroller. And sensor basically does simple data acquisition and signal conditioning. So you would output digital, in digital form, your acceleration and angular rate. Nothing more than that. So next, came, a variety of intelligent sensors where many of these algorithms, they matured and they started to get added into the sensor. So the very first one was a pedometer. So as you know, if you have an accelerometer, you can take acceleration, and from that you can detect steps, and then you can count them. So pedometer, significant motion detection. So if a package is picked up and moved around, you can detect that using an accelerometer. And that logic, once it becomes mature, why do you need to run this in a microcontroller? You can run the logic in the sensor itself. So it started to get it added into the sensor. Wake up, free fall detection. So in early 2000s, as you can imagine, or your laptops had hard disks, and if laptop were to fall, and if you had an accelerometer in the laptop which could detect that it's in free fall, you could park the head of the hard disk, thereby prevent damage to the hard disk. So that was one of the other algorithms that got embedded inside the sensor. And then 6D orientation. Next came this idea of sensor fusion. So sensor, instead of outputting raw acceleration and angular rate data, it would compute your orientation, your Euler angles or your quaternion on the sensor itself. And it'll output quaternions or the Euler angles over in the digital form over to the microcontroller. Next one was addition of a finite state machine. So I'll talk a little bit more about what exactly is a finite state machine and how does it help when you are dealing with sensors in determining context. So main idea is that you can put thresholding logic in a finite state machine and you can traverse through different states. So that is the role of a finite state machine embedded inside the sensor. So just a simple idea, to detect if your phone is sitting face up or face down, you can do that using a finite state machine because those are two different states. And you can traverse from one state to the next state by looking at the gravity vector. The next thing that got added was machine learning core inside the sensors. So now here, this is where the real intelligence, beyond the simple finite state machine starts to get added into the sensors. And what does a machine learning core do? Machine learning core has a capability to run a decision tree inside the sensor. So as you know, decision tree is a pretty powerful algorithm when it comes to machine learning, different algorithms among the portfolio of machine learning options. And if it can be executed inside the sensor, the biggest advantage you get is extremely low current consumption. Because there are two things that happen. I'll talk a lot more about that in detail, but there are two things that happen when you run the logic inside the sensor. You do not need to transfer all kinds of raw data from the sensor to a microcontroller or to the cloud or whatever it may be. You do all of your computation inside the sensor. You only output the classification results or context change from the sensor. So you are saving energy that is being utilized to communicate this data over your serial bus like I2C, I3C, or SPI, whatever it may be. That's number one. Number two, you do not need to keep an application processor or a general purpose microcontroller awake all the time, processing the raw sensor data that is being sent to the sensor, from the sensor to the MCU. So that's where you gain. So your overall system efficiency improves significantly. So I'll go through this and show you math on how this system power efficiency is achieved. And the machine learning core, there is another, so these devices that I'm talking about, finite state machine, machine learning core, and ISPU, these are available in IMUs and accelerometers from STMicro. So, as I briefly touched upon this topic, there are two different system paradigms. So one paradigm is, you would have compute that occurs, on the microcontroller, or in case of centralized computing on cloud. So you would have, data being sent out to the cloud from, all of these devices, which could be your car, your robot, your, wristband, whatever it may be. So large amounts of data is sent over the network to the cloud. And then there are some time-sensitive applications, where latency is very important from the perspective of a user. Those applications tend to have a problem when you have to wait a while for the data to be processed on the cloud and the results to be sent back to the device where the user expects the results instantaneously. So that's where the paradigm has changed. So in case of edge computing, the paradigm is you essentially are going to do all the processing as close to the edge as possible. So there are different notions of edge when people say edge computing. One notion is that you would some devices that have an application processor that is in your device, like your mobile phone. People would consider that to be the edge. Others would say, okay, there's a microcontroller that's connected to this application processor, and microcontroller is further away towards the edge. So my MCU is the edge. Then, others would say, okay, sensor. Sensor is actually sensing the physical world. And if the computation occurs in the sensor, that's the true edge. So it depends on what definition you want to use. But in case of edge computing, the idea is, your computation occurs inside the sensor. And that is, in some cases, people would call it edge of the edge. So let's talk about machine learning core and finite state machine. So in case of finite state machine, here is a block diagram. So essentially what, I have to be careful. Standing in midst of a bunch of cables that are sensitive. In case of finite state machine, this is a behavior model, where you can transition between different states. So, what I would describe as a finite state machine, an example of that would be something like this. Imagine you have an accelerometer in your phone, and this accelerometer can detect, you are in your car. It can detect that you are in a car and the car is moving, because that's a specific motion pattern for car, right? Now car comes to a stop. So that's a change in state. Your state changed from driving to stationary. Next is that you get out of your car and you start to walk. So accelerometer can detect that you got out of your car and you have started to walk. So those are two other states. A finite state machine can do this for you. So finite state machine can then tell you, okay, this is where you parked your car. So a higher level application then can use this information and bring you back to where your car is in a parking garage in a shopping mall. So that's how a finite state machine can be used to traverse between different states. So what does it have? So first thing that it needs is, of course, sensors. So generally sensors with accelerometers and gyroscopes that support finite state machine would take that data. But in some cases, you have a possibility to also add external sensors. So you can connect a magnetometer or a pressure sensor to the auxiliary interface to such a sensor, and bring in this additional data to be processed through the signal conditioning block. And then you essentially can run this through a finite state machine block. So finite state machine block will compute these thresholds and then do these comparisons and then determine which state are you in. So next is machine learning core. So in case of machine learning core, you are not confined by these thresholds. But in case of machine learning core, you can actually run a decision tree inside the sensor. So the architecture is somewhat similar. So you have your sensors, accelerometers and gyroscope. You also have a possibility to bring in an external sensor like magnetic sensor or pressure sensor, humidity or temperature if you want to add those. And then you have a computational block inside machine learning core, which is able to apply filters to the sensor data. So let's say you have XYZ axis of accelerometer, XYZ axis of your gyroscope, XYZ axis of your magnetometer. You can process any of these axes through a defined filter, or you can apply a filter to norm of acceleration, norm of angular rate, norm of magnetic sensor or pressure sensor. And then this computational block also has an ability to run predefined features. So as you know, if you're trying to build any algorithm, you would use features such as mean or variance, maxima, minima, peak-to-peak value, energy in the band, all of those features. So those features can be computed inside this block. So as you can imagine, you achieve great efficiency if you are computing these features inside the sensor and you're not using a general purpose microcontroller. It's fairly simple, right? You don't need a general purpose microcontroller to compute mean or variance, right? It can be, all of this logic can be embedded into gates. So that is the advantage of machine learning core. You can execute a decision tree inside the sensor. So you also have a possibility of adding a meta classifier. So what does meta classifier do? It smooths the output of a decision tree. So once we get more into a discussion on this, you'll be able to see the advantage of each of these features. So diving a little bit more into it, finite state machine and decision tree, just to give you comparison between these two. If you compare, what can a finite state machine do and what can a machine learning core do? So FSM can go through a finite number of, predefined states, and it can transition between these different states. As you would remember, the example that I talked about was person driving and, parking their car, getting out of the car and walking away, right? So those are different states. You can do this logic in finite state machine. But machine learning core can run, your predictive models like decision tree inside the sensor. So, these decision trees are built up of nodes, which each node will have if then and else condition. And each node will have one or more features on which these if then and else conditions are applied. So if you traverse through the series of nodes, at the end of your traversal, you will arrive at some classification. So I'll walk through this and actually show you an example. So those are the two differences between finite state machine and machine learning core. So just a little bit of background on this. There are a large number of traditional machine learning algorithms, supervised or unsupervised. So, and then under supervised category, there are a bunch of them like regression, classification, naive Bayes, support vector machine, KNN, all of those. So under classification, this is where you will see decision tree. So decision tree is that type of algorithm that can run inside ST's 6-axis IMU, both consumer grade or the automotive grade, accelerometers or inclinometers. And as I was saying earlier, you can also connect a magnetic sensor to this IMU, which has machine learning core in it. You can also connect a pressure sensor to it. So each node essentially would have, an input condition, and then, you will have those if then and else condition inside each node, and then the output would be a true path and a false path. So as you traverse along true path, you will arrive at some classification. So diving a little bit more into it, we talked about this. The sensor data is the first block. So inside that, you have an accelerometer or gyroscope, or you can have an external sensor. In the computational block, you have, computation occurring to filter your data. Remember, sensor data, it goes through a data acquisition chain, a signal conditioning chain, and then you can apply your own filter to it. So filter could be your high pass, band pass, low pass, whatever, notch filter, whatever filter you choose. I'll describe that a little bit more in a few slides. So you can apply the filter inside the sensor, and then you can compute features. So these features would be, a variety of such, features that I talked earlier about, mean or variance, energy in the band, peak-to-peak value, zero crossings, all of those, they can be all computed inside this block. Then decision tree could execute using these features. And finally, you can apply a meta classifier before you make the results available from the decision tree. So all of this is happening now inside the sensor. So let's talk about the sensor data input. So sensor data input can contain, X, Y, Z axes of acceleration. You could have norm or norm squared for the acceleration. Similarly, for gyroscope, you could have X, Y, Z values of gyroscopes that can be used in your decision tree processing. You can have norm of gyro or norm squared of angular rate as well. Same thing for magnetometer. So all of these can be your input. You can choose, in some cases, just Z-axis of accelerometer is enough. But this is where the application part comes in. Next is your filter. So, you can put a second order IIR filter inside the sensor. So why IIR filter? Because IIR filter for real-time implementation is very, very effective. You can create pretty much anything out of this thing, a low pass, band pass, high pass, notch, whatever, a combination thereof. As long as you can define these coefficients, B1, B2, B3, and A2, A3 along with the gain, you can create any filter you want to. So you can use MATLAB or your favorite tool. design your filter, and come up with these coefficients. This sensor will take your coefficients and apply that filter to the selected axes or a combination of those axes. You can do more than one filter. You can do XYZ axes plus the norm, or only Z axis plus the norm, whatever the choice may be. Next is all the features. So there are 31 features available inside the sensor, and they are mean, variance, energy in the band, peak-to-peak value, zero crossings. It has both sensors, positive and negative zero crossings. So as you know, to arrive at zero crossing, you would use some thresholding, right? So that's available to you. Peak detectors. In many applications, peak detectors are important. So there are two types available, positive peak as well as the negative peak in your signal data. And then minima, maxima. So there are 31 such features. So this is a typical decision tree. So essentially, you will start with the starting node, and then you can traverse down all of these different nodes. So you can run up to 8 decision trees inside, this sensor LSM6DSRX. And you can have maximum of 512 nodes. So as you can see, there is a constraint here. You cannot put anything you want to. You have, a capacity limit of 512 nodes. But just to give you an idea, if you want to do human activity recognition as a problem to solve using this kind of a sensor, it can be done in about 60 or 70 nodes. So 512 nodes is plenty to run multiple such decision trees inside the sensor. Another sensor, LSM6DSV16X, that's available. This is also an IMU. It has a capability to run 8 decision trees with a maximum of 256 nodes. This is a smart accelerometer, ultra-low power accelerometer, LIS2DUSX12. You can run 4 decision trees inside the sensor with a maximum of 128 nodes. So next is, what are the key steps in machine learning implementation and development of your algorithm? So there are essentially 5 steps. So the very first step is that, as you know, machine learning is all driven by data. So you would capture all kinds of data. Then, you would label this data, you would design your filters, you would design your features, and from that, you build your decision tree. And then you embed this decision tree in your sensor. And then, process this in runtime, and you basically get your whole solution. So how can you do this in real world? So there is this tool, MemStudio, which I will talk about. And I will do this example using MemStudio. MemStudio will do all 5 of these steps for you. You can download this from st.com. So MemStudio can be used to capture labeled data. So there are devices like this that are available. This is a sensor tile. So sensor tile essentially contains all kinds of sensors in it. It has about 6 sensors. So when we get more into the presentation, you'll learn a little bit more about it. But it can be strapped on your wrist if you want to do an experiment where, like, for your smartwatch type application, it can be attached to a machine to do vibration analysis kind of application. So you would capture data. Then you would label the data using MemStudio. You can generate the decision tree using the built-in tool inside MemStudio to take this data and then from that generate the decision tree. And then finally, MemStudio will give you your decision tree in a form that can be embedded inside the sensor. So that can be part of your header file. If you have your sensor connected to a MCU, a microcontroller, so for your embedded code, you would use the header file and then the decision tree inside that for initialization of the sensor. Download that into the sensor. And then, you can monitor the data, using MemStudio in real time if you have a device like this. So, one example. So, this is a common example that is used in machine learning, is to build a human activity recognition. So, as you know, accelerometer data, it can be used to detect whether you are walking or you are stationary, if you're riding your bicycle, if you are in a car, bus, or train. So all of these, different modes, the very first thing that you will do is to define your classes. What are the classes that your decision tree should classify? So classes can be stationary, walking, running, jogging, biking, transportation mode like car. Next is, collect data. So the data can be collected, with a device like this, as I was showing you earlier. You could carry this device with you. It could be on your wrist. It could be in your laptop bag. You collect lots of data, and collect data with large number of people, diverse group of people, men, women, people tall, not so tall, all of that. Bring in diverse amounts of data, and then properly label it. Remove any the data that the log file that contains walking should only contain acceleration data for walking. It should not contain data for driving, for example, right? That's how the classification logic will be built. So do the pre-processing, clean up all the data, label it properly, and then process this. Then next thing would be to define your filters and features. So one simple thing. If you have to detect something is stationary or moving, you can use a simple feature like variance. Variance will increase the moment acceleration is higher because variance corresponds to energy. When the device is sitting stationary, variance will be low. It will only correspond to the noise of the sensor. But when you start to walk, variance will be higher. So you do your feature engineering. You pick up your features. So you picked up your features, and as you know, machine learning works best if you give it as clean a data as possible. So apply your filters. So look at your sensor data and design a filter. And this design of the filter could be done using your favorite tool, MATLAB, whatever it may be. And finally, you can produce a decision tree. So using your tool like MemStudio, you could use Vecca, you could use RapidMiner, you could use any of these tools. Scikit, if if you use Python a lot. Design your decision tree, then embed that onto the sensor. So those are the 5 steps of actually building the full solution, starting from capturing the sensor data to creating a complete solution. So now let's dive into some examples of what has been done. So I'll talk about some examples. I'm using in this case a scenario of personal computing devices. All of us use laptops. So using an accelerometer with a capability to run a decision tree inside the sensor, you can detect whether the laptop is in the bag or out of the bag. You can detect whether the laptop is on the table. You can also detect if the laptop has been picked up. This gives you context. So the context scenarios that you have here can improve user experience. And how? In this case, if you can detect your laptop is in the bag, but laptop has not gone into hibernate mode. As you know, it has happened to many people, right? You shut the lid, put the laptop back in your bag, laptop stays on. It does not go into hibernate mode. It'll overheat inside the bag, drain your battery. Next morning, when you pull out your laptop and you try to power it on, battery is dead. And maybe if you had something else in it, it could damage that because of all the heat generated. You can detect, by running this algorithm inside the sensor, you can detect that the laptop is in the bag because there is a specific motion pattern when you put this laptop in the bag and walk with it. So, this will work for all the scenarios, like, when you're stationary or you're walking or running or, you're in a transportation mode, like bus or car or bicycle. The biggest advantage is that this algorithm running inside the sensor consumes only 37 microamps. And laptops, application processor, in this case, whatever the processor is, that processor will be off. But the algorithm can run inside the sensor all the time. Same thing for out-of-bag detection. When you take the laptop out of the bag and you are ready to start working on it, ready to log into it, this algorithm consumes only 7 microamps of current. So for those of you who have done math on microcontrollers and application processors, you know that to run an algorithm like this, processing sensor data on that application processor, it will be hundreds of times more than this current consumption. Same thing for on-table detection or pickup detection. So 14 microamps of current consumption when the algorithm runs inside the sensor. 5 microamps of current consumption when it runs inside to detect pickup. So many of these algorithms are available on GitHub. They can be downloaded from st.com, and a link is available on st.com. for all of these different algorithms. So, industrial, there are applications for detecting status of a drilling machine. Is the drilling machine on, off, or is being used to drill? Gym activity recognition can be built using this. Smart access for automotive, whether the vehicle is moving or stationary, those kind of applications. So, in-back detection, as I was saying earlier, so this is a combination of machine learning core, which detects the in-back carry condition, and finite state machine. And it will work for all of these scenarios. So 37 microamps of current consumption. This is actually, enables building sustainable consumer devices. And how? So if you were to save, this draining of the battery when the laptop is in the bag and you basically detect the in-bag condition and do not drain the battery, you'd be saving 70,000 tons of carbon dioxide if you use this sensor and detect in-bag. Because the math was done for about 260 million laptops that are in use in 2023. And it takes 8 hours to drain this battery, essentially. So that much energy lost for 260 million units of laptops all around the globe, you'll save 70,000 tons of carbon dioxide emission. If you were to do the math of why this is making sense, on the left-hand side, we have implemented the algorithm for activity recognition using the accelerometer, where the algorithm runs on a microcontroller. So in this case, we are using a Cortex M4. The sensor will consume about 15 microamps of current. As you can imagine, in this scenario where the algorithm runs on the microcontroller, machine learning core is not used. And MCU, you're waking it up once every 16th of a second, or every 63 milliseconds you wake up the microcontroller. So the current consumption is about 51 microamps. So total is 66 microamps to do human activity recognition in the software implementation when the logic is running on the microcontroller. Now looking at it on the other side, when the activity recognition logic runs inside the sensor, sensor will consume the same amount, 15 microamps, but machine learning core will only consume 4 microamps. Add this up for a microcontroller that wakes up once every 30 seconds, about 0.65 microamps. So total is about 20 microamps for the same feature. So it's about 3 times less power consumption when the algorithm is implemented inside the sensor. There are many examples. So if you're looking at examples, for human activity recognition for a smartwatch, 6 microamps of current consumption. Gym activity recognition, another 6 microamps of current consumption. So sensor runs all of this logic. MCU or the application processor connected to the sensor does not need to do anything. It just basically needs to deal with the classification result. Wrist tilt, when you tilt your wrist and you're looking at the face of the smartwatch, that's when it should light up. So this algorithm, 16 microamps of current consumption. To do swimming style detection, this algorithm can run inside the sensor. Machine learning core can do it. A decision tree can do this. So about 8 microamps of current consumption. Sleep detection, 1 microamp of current consumption. So 8 hours of sleep, MCU does not need to do anything. In the smartwatch, sensor is doing all of this for 1 microamp of current consumption. So the main idea here is, this approach allows you current consumption optimization on the system level, at the system level. So increased battery life. Nowadays, everybody wants to have 1 week of charge. You should charge your smartwatch once a week, not every day. So how can you achieve that? You can achieve that by moving the algorithms like all of these closer and closer to the edge as you can, and thereby improve the efficiency of the system. So now let's talk about the AutoML part of it. So in case of AutoML, the first question that arises as to, what is the advantage? So machine learning core, as you know, it has its own limits. It can support only a given number of features. It has a given number of nodes, and it has, a certain window size that it can operate on. So any decision tree, it will operate on a certain window size, right? You will take a window size of, let's say, 1 second, and you will look at the sensor data that is available in that 1 second window, and you will compute mean, variance, energy, whatever those features are, and then process that in the decision tree that I talked about. So all those if, then, and else conditions at each node, and finally you arrive at the result. Are you walking or running or jogging, right? So you can do all of this, but you have limitations on how much window that you can deal with, what are the filters, features that you can implement. So this is where the AutoML tool that we have built called as AFS comes into picture. It will automatically do all of these for you. So this is our no-code AutoML framework that's available inside MEM Studio, which will automatically select the best set of features. It will automatically pick the best filter that you need, and then get you to the point where it can generate the decision tree for you. So the whole solution. So how does it work? So here is one slide that shows this framework. So you start with, of course, your labeled sensor data. So you have collected all of this data, walking, running, jogging, if you were to build a human activity recognition type application. If there is a need, you could resample this data. But then the very first thing will be to do filter selection. So there are two approaches that we offer, a basic approach or an exhaustive search. Then we automatically provide the window length calculation. So I'll walk through an example to show you how this whole thing works, how this is a purely no-code implementation. So you don't need to write any code for this. The tool can do this for you. And then automatically pick the features. So there are a variety. This is an ensemble of methods that are available. A random forest or ANOVA or AdaBoost, a sequential feature addition, recursive feature elimination. All of these methods go into picking the right features. Remember, there are 31 features. You need to pick the right combination of features for what you are processing in your sensor data, right? So this will allow you to do that. So once these three pieces are done, then this thing ARFF file will be generated from this. You will process this through and generate a decision tree out of this whole logic. And finally, the decision tree that is generated out of the tool, either this tool or you could use your own favorite tool to generate the decision tree. Whether it's a Vecca, RapidMiner, MATLAB, whatever it may be. Or you could do all of that in MEM Studio. Ultimately, you will produce the decision tree that can be embedded inside the sensor. So I'll walk you through this really quickly. So the very first thing is automatic filter selection. So, only few equations in this whole talk. This is one of them. So as you know, this is your transfer function for a filter. This is an IIR filter, second order IIR filter. So you have your numerator coefficients, denominator coefficients, and a gain. So this is what you need to determine for your filter. It could be your band pass, low pass, high pass, notch, whatever it may be. And you can apply that to any of the axes, as I was saying earlier, X, Y, Z axes, norm axes, a norm of the axes, or a combination thereof. And there are two algorithms, basic and exhaustive. So the basic algorithm, let me describe that using a power spectrum. So here, I'm using this example of human activity recognition. So there are 5 states: stationary, walking, fast walking, jogging, and biking. So if you compute the power spectrum, you see the largest amount of energy is in the class corresponding to jogging. And you can see the frequency band for jogging. Then you see the frequency band for walking. And then you see frequency band here for, in this case, this is a second peak for jogging. But somewhere here is biking. So you would look at the average energy. You will pick all the relevant peaks above that average energy. And then you will identify the maxima of the signal in that frequency spectrum and pick the filter for that. So a basic search will look through your power spectrum and figure out, okay, if I have to get rid of everything, I just care about this band for jogging. Everything else is noise for me when I consider jogging, right? Similarly, for walking, I should only look at this orange trace here and then filter this data. Everything else is not meaningful for me. So you basically do a quick search and automatic filter selection algorithm will give you the filter for this particular scenario. In case of exhaustive search, what the algorithm does is it uses entropy-based method, and it searches the entire spectrum and then finds the frequency of interest. Next thing it does is basically minimizes the filter, which ultimately it minimizes the entropy for the filter that you have selected for the selected class. So let me repeat this. So entropy reduction means that you have found the filter that gives you maximum signal. So that's what this method does. But this method, as you know, it's scanning the entire band, so it is exhaustive, which means that it takes longer than the basic search. Next is the window length determination. So in case of window length, again, as you know, you have to operate over a window of data, right? You will compute features for a window of data which is 60 seconds, 60 points, 30 points, whatever it may be based on your selection. So I'll walk through an example and it will become clear. So the window size can range anywhere between 1 and 255. So I explain this again using that same power spectrum. So, same classes, stationary, walking, fast walking, jogging, and biking. So, what you do is you look at the very first significant peak in your power spectrum. So in this case, it is at 1.8 hertz. When you're walking, your walking rate is about 1.8 hertz. So you take 1.8 hertz, divide that by 2, and then, invert it. So it becomes 1.1 seconds. So that's your window duration. Now multiply that by a factor of 2. So that's 2.22 seconds. And if your sample rate is set to 30 hertz, 67 samples. That's how you arrive at your window length. So 67 samples of data, you will compute all these features, you will apply the filter, and then you essentially now are ready to do your classification. Next is features. In machine learning algorithm, this is one of the most important parts, feature engineering. So in features, the machine learning core supports maximum of 31 features. Mean, variance, energy, peak to peak, maxima, minima. And then there are these features that are threshold features, which are zero crossings, positive and negative, number of peaks, positive or negative. So we have an ensemble of methods that essentially can be used. So in this case, thresholds, for example, how do you determine what is your zero crossing threshold? How do you determine when you traverse, because as you can imagine, zero crossing is triggered by something. It's not just zero, right? If you set a threshold, it is more meaningful. So these threshold features are selected by doing the highest accuracy through cross-validation of all the threshold features. So let me explain this. You pick a feature like this, in this case, zero crossing, and then you vary the threshold. The algorithm varies the threshold and then arrives at what is the best value that gives you highest accuracy. And then that feature is selected for that particular threshold. This framework essentially is giving you access to 6 of these methods. So let me describe this to you. So you can take an approach where you take all 31 features, right? You pick all of those 31 as the features, and then generate a decision tree. Your algorithm, essentially, to generate a decision tree will do optimization. So you have a large amount of labeled data. This labeled data is processed through that optimization algorithm, and it will give you an accuracy for a decision tree using those features. So now you remove out of 31 features, 1 feature. Out of 30 features, then you again obtain the accuracy. Compare the accuracy between the two. So you can traverse this, starting from 31 going all the way down to 0. So somewhere in the middle, you will find that your combination of those features will give you maximum accuracy of the decision tree. That is your set of features to use. So the process I just described to you is recursive feature elimination. You can do the reverse. You can start with 1 feature, compute the accuracy of decision tree, and then keep adding features. Start with mean, add variance to it, add energy to it, add maxima to it. So you can do recursive feature addition and sequential feature addition and arrive at, again, a combination of features. And the other thing is you can use ADA boost. That's another approach. You can use random forest, a combination of decision trees, and arrive at finally what are the best features. So this ensemble of these methods allows us to get you the best possible combination of features. So now once you have done this, I want to show you, how well does it work. So there is some benchmarking that we have done for human activity recognition application. So in this case, the data that was used was accelerometer data and gyroscope data for 9 activity classes, and we used a publicly available data set called as Auritus. So Auritus contains data for walking, jogging, jumping, sitting down, lying down, standing, turning left, turning right, and falling. And this was 2.7 hours of data with 45 users. And the sensor data was sampled using a ear-worn device like your Apple AirPod. Data was sampled at 100 Hertz rate. And we used decision tree inside the machine learning core. We used random forest implementation on a microcontroller. And we used XGBoost, which was implemented for a smartphone. We used Light GBM, which was again an algorithm that can run on a smartphone. So what we find is decision tree, essentially outperformed all the other approaches. We were able to achieve 93% accuracy for under 1 milliwatt of power. It outperformed other classifiers by 7 to 21%. So all of these details are in a paper that we published in IEEE Sensors letters. There's a link available in this package that I had shared. So I think this PDF is available to you, right? The PDF of this presentation, I had sent this beforehand. So the link is in that. If it's not, I'll figure out a way if you are interested in that paper. So 35% higher accuracy. The runtime was 45 times to 2,400 times lower, as you can imagine. XGBoost is a very expensive algorithm. If you run this on a smartphone, it'll take a much longer time than a decision tree. In case of decision tree, you're just traversing through a bunch of nodes and arriving at your classification result. Power consumption. When you consider that for a Cortex-M4 implementation, 41 times to 137 times lower current consumption for human activity recognition when it is implemented inside the machine learning core in the sensor. So we talked about MLC. Now another flavor of this is ISPU, Intelligent Sensor Processing Unit. So ISPU is a unique solution for TinyML from ST. What it allows you to do is run your C code on the sensor. Now this is also, again, not a general purpose microcontroller, but it is ISPU is based on the STRED architecture. This is a ST proprietary architecture. Extremely low power consumption on a very small silicon area. So ISPU can run any type of processing logic from basic signal processing to AI algorithms. You can implement your sensor calibration logic to, you can implement a BNN, binary neural network on ISPU. It has a 32-bit RISC Harvard architecture. But it has 2 clock settings, 5 megahertz or 10 megahertz. Has an FPU, has 2 RAMs. So as you can see, this is the constraint. How can you achieve good power efficiency? You're constrained by how much memory you have, how much you can operate on. So 2 RAMs, 32 kilobytes for code and read-only data, and 8 kilobytes for variable data. And it does not have an NVM. So each time you initialize the sensor, you have to, again, download your code into the sensor. So this is a brief look at what essentially you can do inside this. So you have your ISPU, which interfaces with external sensors, which can also interface with external sensors if you want to connect over an I2C bus. You can interface with an external microcontroller over SPI or I2C bus, and then there are a bank of registers that you use to communicate, essentially, to bring the output from the sensor. So ISPU, there's a tool chain for this. You can use TensorFlow, you can use any of these to generate your network, and then from that you can convert that into C code, and then there is this ISPU tool chain, which will generate the ISPU.srec And that can be converted into a file which will be downloaded inside the sensor. So this particular tool chain will give you your C, C++ compiler as an assembler, as a linker. We also have a bunch of C libraries, C++ libraries that are available as a starting point. You can use those. These are all available from GitHub. Here in your PDF that you have, maybe you can see this link. Or you search on st.com and you can find it. So it can work on Windows, Linux, or Mac OS. The libraries that we have put together for ISPU include your accelerometer, gyroscope, or magnetometer calibration libraries, sensor fusion, activity recognition, pedometer, wrist tilt, fall down. Those kind of features are all available. Same thing for decision tree. As I was saying earlier, on GitHub, everything is available to try out. There are many examples that we have put on GitHub. So, here are some of the libraries for, sensor fusion, 6-axis or 9-axis. For wearable, these kind of solutions are available. For industrial, outlier detection, vibration severity detection, that can all be done inside the sensor. So now, we have talked about all of this. Let's go through an example. So the idea here is to go build a complete application. So I'll walk you through this using our tool called as MEM Studio. So you can actually download MEM Studio from st.com and do this all by yourself. Fairly easy. There are a bunch of tutorials, there are a bunch of videos that are available on st.com for you to try. So MEM Studio is a desktop software application which gives you a complete experience of collecting sensor data, visualizing sensor data, developing your AI algorithms, trying out your embedded features and libraries, analyze this data, do your no-code, low-code implementation, and basically touch all aspects of the embedded software development, signal processing, and AI development. So the whole story starts with sensor configuration. So the very first thing that you would do is sensor configuration. So MEM Studio will give you access to the full register map. So you can look at the data sheet, figure out how to configure the sensor for its desired sample rate, for its desired dynamic range, for the power mode. You can be in low power mode, normal mode, high performance mode, any of those power modes. All of that can be accessible through the register map. You can configure your interrupts. You can do sensor data analysis. So you can look at your data through line charts, bar graphs, 3D plots. MEM Studio does that for you. You can do time domain or frequency domain analysis. You can look at FFT of your data. So I was showing you a power spectrum for the use case of human activity recognition. So this can be done using MEM Studio. So those pictures that you see can be generated by MEM Studio. You can do spectrogram analysis. It gives you spectrogram feature. The next part is application development. After you're done your analysis of sensor data, to test your features such as your embedded pedometer, if you want to use that, free fall detection, if you want to use that, or how do you configure the FIFO inside the sensor. All of that is available through MEM Studio. Of course, you can also use this for in-sensor AI and ML algorithm development. And I'll walk you through one example. You can visualize all of your data. You can do your data logging. As you know, first thing for any machine learning algorithm, data collection. Not only data collection, high quality data collection. The better is your data, better is your algorithm performance. So high quality data collection, all of that can be done using this. And then you can play with the approach of no-code algorithm development for STM32 microcontrollers. You don't need to write a single line of code to make your algorithm work on an STM32 microcontroller using Algo Builder, which is part of MEM Studio. So for sensor configuration, the first thing you would do is, of course, you would connect your board. So there are many options. So I brought a few with me. You can come by and see this later on. We have a Nucleo board and a sensor shield. So this is the Arduino approach. You can stack your shields on the bottom board, which contains your microcontroller. This is one of the boards that can talk to MEM Studio. The other one is your sensor tile. And the third one is your something like this. So this, has, it'll connect to your desktop device, your laptop. The next thing would be, you would have access to all the advanced features inside the sensor. You can evaluate your configuration. You can acquire your sensor data. Next would be your sensor data analysis. What you log. You can do analysis using MEM Studio. So visualize the data, label the data. We will label the data in this exercise. I'll walk you through how you label the data. And then, you can do FFT. You can run a spectrogram on it. You can then generate your firmware code. So, this is all done graphically. So AlgoBuilder gives you capability where you can take existing libraries like calibration library, sensor fusion library, and drop that onto a palette, connect everything up, and it will generate the entire code for STM32 microcontroller to which this sensor is connected. So application development also can be done by this. So this can be, all of what I'm talking about can all be downloaded from st.com. There is a data brief available, there's a user manual, and there is a ST community where, people ask questions and, there are experts who answer those questions. So this is all available. So I've already shown you these three. So this is your STM32 open development environment, which is and then this is the sensor shield that sits on top of the Nucleo board. So it's, we support all kinds of microcontrollers. So F401, is supported on this Nucleo F401, U5, the latest microcontroller that we have with this sensor shield. And there are a variety of sensor shields that are supported. This, professional MEMS tool that I was talking to you about, you can essentially on this slot, you can put any ST sensor in the DIL24, adapter. This will all fit here. So in this case, that's what it looks like. And then finally, this is the SensorTile.box Pro. So it's an all-in-one wireless node. It has BLE, Bluetooth. So you can have BLE connectivity to your mobile phone or your laptop. If you're doing your data collection on your mobile phone or your laptop, it even has an SD card. So you can keep the data inside the SD card, and later on, after you're done with the acquisition, connect that to your laptop and extract the data. So, the very first thing that you would do when you start up MEM Studio, it comes up with a palette like this. So you'd open the settings here. So first thing is connect, and then even before you connect, you go to your open settings. And open settings brings up another screen like this. So what does it do? It gives you all these options. You're starting from something fairly simple, like the color theme that you care about, light, dark, legacy color themes. You can use any of the color theme that you feel comfortable with. Here your plotting grid, it can be stationary or moving or rolling, depending on how you prefer to look at your data. You can enable registers, which will essentially automatically read the registers. So when you connect your board, all of the registers will be read automatically in the register map page. Here are the units. So you can configure the units. So accelerometer data, accelerometer units, gyroscope units, magnetometer units, like milli-G, milli-degrees per second, milli-Gauss, degree C, humidity, pressure, all those units you can configure here. This is going to be very important. If you don't get the right units, your analysis, your filter definition, your feature definition will all be impacted. So you set the proper units here. You can do multiple pages, docking or undocking. So this is a feature that's available. If you connect your ProfiMEMS board, it will automatically do an easy configuration for you. The easy configuration is going to set up the dynamic range. It's going to set up the sample rate. It's going to set up the power mode, all of those automatically. And you can change the text size, whatever, the look and feel of the application. Next is the updater. So we keep updating MEM Studio. So how do you do this updater? So there can be an automatic update. It will update your application. As you know, if you install this on your device, you need to have proxy settings. So there is a section for proxy settings. And then, there's a button here, check connection. So it'll check the connection to ST and bring the latest update to MEM Studio. So, essentially this page for updater will do that. Next is AlgoBuilder settings. So as I was telling you, Algo Builder will allow you to take a large number of libraries that are available on ST for sensor calibration, to sensor fusion, to activity recognition, to whatever. So you can use a combination of this and build your application. You can also bring in the machine learning features like decision tree into this. So there are three options. You can work with, you of course need one compiler, right? So you can pick one of these three. So you can use IAR, or you can use Kyle Microvision, or you can use STM32Cube IDE. So you need to specify the path as to where is this compiler on your machine. And then of course you will need an STM32Cube programmer. That's how you would download your decision tree or your embedded firmware to the microcontroller. And there is this also option, filter build output. As you know, if you're using a compiler, it'll generate all kinds of output. So this will automatically, filter the output and show this to you in one of the output windows on MemStudio. So the boards, you can only connect certain boards to it. The supported boards, like the ones that I was showing you, these are the only ones that you can connect to MemStudio. And you must have the proper firmware. As you know, this board needs to talk to MemStudio, right? MemStudio is running on your laptop. There's a firmware running on the sensor tile microcontroller, which has, of course, BLE as well. So you need to have the right firmware. And this is all defined. This is all described in the tool as well as our data brief. And you need to use a compatible USB to PC cable, or if you prefer to work with Bluetooth, you need to specify that. So there are two ways to connect your device to the laptop. One is USB, other one is BLE. So this is your connect page. So you arrive at connect page, and you basically select this connect button. What it does for you is brings up this particular page. If you're using Algo Builder, you can have BLE as one of the connection options for you. Otherwise, your communication type is a serial interface, which is your USB. So you need a USB cable, essentially, to connect sensor tile, or to connect your Nucleo board or ProfiMems board to the laptop. And then it will automatically detect your communication port, so COM port. If it is this, if you're using the USB, it will automatically detect the COM port. So once you connect the device, this button will change to disconnect, and all of your device will be initialized. All of the sensors and everything on the device will be initialized by MemStudio. If you connect a ProfiMems board, it will give you a choice of the device that you want to connect. So, whether it is a 6-axis IMU or an accelerometer or, environmental sensor or your magnetometer, gyroscope, whatever it may be, you can choose in case of ProfiMems. So, the board, the DIL24 board that you connect on this with the sensor, that's what it will show up here as. But if you are using your sensortile.pro with a data log extended firmware on it, it will automatically detect and populate the sensors inside this device. So this device has a 6-axis IMU. So it will automatically show you LSM6DSV16X as your accelerometer and LSM6DSV16X as your gyro. It'll show you that there is a magnetometer, LIS2MDL inside it. It'll show you that there is a pressure sensor, LPS22DF inside it. It'll show you that there is a humidity sensor and a temperature sensor inside it. So, once you connect this device, there is another page that shows up with the figure of the device that is connected. It will show you your sensor tile, and it gives you all of these resources here. So you have a link to this device on st.com. It'll give you a link to the data sheet for the device. It'll give you an application note for the sensor, for the finite state machine, for the machine learning core. It'll also give you a link for the GitHub, for the platform independent driver for this sensor. It'll give you a link for GitHub for the finite state machine examples, for machine learning core examples. Similarly, for all of the other sensors, it gives you all of these links. So you have all of this material that you can just access from this one connect page, all of the collateral. Once you are connected, now let's go into the advanced feature of machine learning core. We're going to, remember, we have to do machine learning part on the sensor, right? So there are 4 things that you can do here. One is your data patterns. As you will collect data for all these different classes that you selected. Walking, running, jogging. I'll keep using that same example. Your classes can be anything that a sensor can detect. And this is the part that you as the designer need to do, which is to pick your classes. In case of human activity recognition, your classes are walking, running, jogging, biking, whatever those may be. So you will collect the data, and then you will do your data patterns on this tab. Then next thing, all this data that you have collected, this data needs to be processed and made ready to be fed to the decision tree generation tool and the AutoML tool. And that format is called as ARFF, Attribute Relation File Format. So this is a format that's fairly well known. Most of you might, who work with ML would already know this. So it contains definition of your filters, it contains definition of your features, and every instance of the sensor data. So generation of ARFF file. Next is your AutoML tool. We'll walk through that. How this tool will automatically figure out filters and features and decision tree ultimately. And then decision tree generation. Finally, also the generation of the file that is downloaded inside the sensor. So once you reach this point, it's all done. Now your sensor is ready to classify whatever you want it to do. So, MEM Studio supports all of these sensors that have machine learning core capability. There are a large number of these sensors that you can see here on the list. So, on MEM Studio, you would go to the tab for advanced features, and then you will pick MLC. So open advanced features and select MLC. Once you do that, you will have the capability to do all these pieces that I talked about. So very first thing that you need to do is set up a workspace. So those of you who work with MATLAB, it's similar to that. There's a workspace in which you work, and you save that workspace, and you can reload that workspace, right? You can retrieve that workspace. So workspace, and then, so you specify on your C drive wherever you want this workspace to be. And you provide a name of a configuration file. So this JSON file will contain everything. Whatever you do for machine learning core, it will store this here. And whatever you have saved, you can also import it again. You can browse all the configuration files from your different sessions, different work that you have done, bring this back in here. You can clear the workspace. Workspace will not delete your JSON file, but it will clear all the steps that you have done, all the settings set. And then there is a clear settings. So it will bring you back to the default settings for the sensor. So, clean the slate. And then this open log. Open log will show you all the steps that you have taken. So you can see, if you made a mistake, you can go back to open log and see where did you make the mistake. So data patterns, here is what it looks like. Data patterns page. So here in this case, there are 2 patterns that are loaded, for motion and shake, just an example. And you can call it in motion class. So you load all kinds of files here. So I have loaded, these 3 files here, in motion and stationary files. It shows you the size of the file as well. So as you can imagine, in the data patterns tab, this is where you will see all your data that you have loaded. Next is your ARFF generation. So ARFF generation, you would set up your output data rate for the sensor. We have set this to 30 hertz. And window length, 60. So 60 means 2 seconds of data. You set your sensors, accelerometer and gyroscope, full scale of 2G, output data rate of 30 hertz for accelerometer, gyroscope full scale of 2000 degrees per second, output data rate of 30 hertz. And then essentially here you can apply your filters and you can set your features. And then click this button called the Generate ARFF. So you can do your own, you can do this manually. You can design your own filter and put your coefficients here. You can design your own features out of those 31 features I talked about. Set those features here. and hit generate ARFF, and for the data that you have logged, it will prepare the ARFF file. This file is the one that your optimization engine will process and generate the decision tree. If you're using AutoML tool, AutoML tool will do many of these things for you automatically. All you need is label data. So AFS tool, the automatic filter and feature selection tool, will automatically determine the window length. Remember, we were looking at that earlier with the human activity recognition example. The window length was picked to 2 seconds. So this tool will, for the given data, it will automatically compute the window length for you. It will automatically compute the filters. You will choose basic or exhaustive search for filter, and it will automatically do the features. So features, you remember I talked about. You can use an ensemble of methods, right? Random forest, recursive feature elimination, sequential feature addition, add a boost, any of those. It will do that. The tool will do that for you. So this tool basically gets you completely ready for the ARFF generation. Now this is what the AFS page looks like. So on this AFS page here, the machine learning core ODR, you have sampled the sensor data, so you know what is the sample rate, so you would specify that here. But then you will pick window length and which type of filter, basic or exhaustive, and then features. Once you select this, you hit run, this button here. Once you hit run, essentially you will see a dialog box pop up. It shows, okay, I'm doing my filter selection right now. Once that is done, it will automatically populate your filters here. So you see one filter here. B1, B2, B3 coefficients, A2, A3 coefficients are listed here from filter search. And then, once it is done with the feature selection, it will populate all the features here. Mean, so what you see here, mean, minimum, peak to peak, and energy. These are the features. And then you click this button, apply settings. The moment you click apply settings, essentially it will bring you to this tab where now you're ready for decision tree generation. So the tool has done all the work for you. It has already done the filters, windows, features, prepared the ARFF file. In case of human activity recognition example, what you need to specify is the output. If I detect output to be jogging, my register setting for the output should read 0. If it is walking, it should read 4. If it is any other, read 8. So you specify that. And then you hit this button, generate decision tree. And that's it. It will generate the decision tree for you. And this is what the result will look like. It will show you the confusion matrix. This is one of the most commonly used tools to see the performance of a classification engine like that of a decision tree. So what you see here is an example for asset tracking. You can use your accelerometer or a sensor node like this for asset tracking. You attach that to your box that you ship. It will tell you, motion, stationary, shaking, stationary, but the box is not sitting, properly, vertical up, vertical down, whatever it may be. So it shows you for this decision tree, accuracy is 100%. And there were 104 instances of the data in this, and all of them were classified correctly. So then moving on, once this is done, you're happy with the results. What do? You basically generate the file that will be downloaded inside the sensor. So that's your UCF file. And if you want to use MemStudio as the tool to see your output, you can basically load the configuration to the sensor button. So if this device is connected either through BLE or through the USB to the laptop, this load configuration button will download that decision tree inside the sensor on this. You can export the decision tree or the file generated using this button, export as. So this is what it looks like. So you can export as, you specify the path here. So now you have your header file. So for whatever embedded development platform you're using, you will have the header file containing the decision tree. And then essentially you're ready to, if you're using MemStudio, load config will get you ready, and you can visualize the output. So in this case, you know, you will, if you essentially are connected to this device and you are walking with it or doing whatever, you shaking it, you shake that box. If it is an asset tracking example, it will show you the output in real time. It shows you the output here, you know, walking or some other state. This is what it looks like. So we can do the entire thing using this one tool. It also, MemStudio also gives you this very unique capability of data injection. What if you have collected all of this data, labeled all of this data properly, created your decision tree, but it doesn't work as expected when you build your device? So what do? You collect data in real time, bring this data, and then on a device like this, you inject that data into the sensor, the data that you have collected already. And you can walk through that and see each step, what is the decision tree doing for you. So that's your data injection. That data injection capability will let you play back your data on the sensor. So, you know, there are multiple things you can do. You know, there are next, all next, run, and next, all of these pause, stop. Those features are available where it will generate the output of the machine learning core for you, for every sample. And this particular table then can be downloaded. You can go look at it, you know, using your favorite tool. You can figure out, okay, if it's an asset tracking example, you can figure out what was happening. You know, was the decision tree doing something wrong at that particular step? So you can go redesign the decision tree and, you know, play with it. So, you know, the data injection is a pretty powerful capability. So let me very quickly walk you through this example of asset tracking using this board, you know, this particular board, a nuclear board with the sensor shield on it. So the very first thing that you would do is, you know, you would connect this board to a MemStudio on your laptop. Once you connect it, it brings up this page here. Then, you know, you select this button, you know, you select this link here, MLC. Once you select this button, MLC, it will take you to our GitHub repository and then you search asset tracking folder. There are already log files that we have collected, and we have stored them there. So these log files are for motion, shake, stationary but not upright. Those log files are all available. You download those log files, and then you bring them to this Advanced Features MLC tab, where you have specified your path for your workspace, and you load all those log files, all those data patterns here. So class label should describe the data pattern, and then load. Once you load, you know, this is what it will look like. There are 4 files in that GitHub link, GitHub location. Motion, shake, stationary but not upright. The box is not upright. It's sitting on face down or something like that. Next, you know, you can do the ARFF generation, where, you know, you specify your, you know, your sample rate, your dynamic range, your filter feature. If you're using AFS, it will automatically do this for you, right? Then, essentially, you generate the decision tree here, and this is what it will look like for those logs. 100% accuracy for those logs. It's a simple example, something to play with. It's available to you, and then you download this. So here you have set your output as motion. My register output should, if my register output is 8, it means motion. If it is 12, it means you're shaking the box. If it is 0, it means it's stationary. If it is 4, it is stationary but not upright. That's a simple example that you can try. So generate the configuration file and load the configuration to sensor these 2 buttons. Once you do that, you know, this is what the output will look like. Stationary, in motion, shaking. This is the classification that is happening by the logic running inside the sensor on this board. So that brings me to the summary. So you've been able to now see that using the capabilities of embedding AI algorithms inside the sensor, you can improve system efficiency. You know, power efficiency, you know, overall system power efficiency significantly improves for wearable applications, for hearable applications, even for an industrial smart node, even for automotive applications. No matter which type of application you build, this has been shown. You know, our machine learning core application is available in a HP laptop. And that's how they do in-bag detection. So high-end laptops, you can buy them today, and what I'm sharing with you is publicly available knowledge. So there are applications for consumer devices, like mobile phones, even for automotive applications. You can detect whether the car is stationary or somebody has bumped into the car, somebody's trying to steal the wheels of the car. This can all be done by a machine learning core, and it's in production with a car company. Is somebody trying to tow the car? There is a feature running inside the car. So remember, you park your, this is very applicable for a scenario like you park your car at the airport and you're gone for 1 week. You want to make sure that you don't drain your battery when you come back, because this alarm application is running on it. So AutoML tool will allow you to develop all of this automatically, determine your window length, select your filter, select your features, and ultimately generate the decision tree for you. So MEM Studio can do all of this for you. So we have about, this brings me to my conclusion. We have about 8-9 minutes for some questions if you have any.